This video is part of the series on a first course in modelling analysis and control, and here we focus on an introduction to PI design. So far then, we've done some elementary analysis of loop performance with just proportional or just integral compensators, and we've established that neither components, if used alone, are sufficient. So this video is going to look at how we might combine the proportional and integral components and simple methods for getting appropriate design values. Some offset assumptions then, just as a reminder. If you have no integrator in the loop, then it's pretty much inevitable you're going to end up with a steady state offset, because in practice your gain is limited. So if you add an integrator to the loop, then you can get a zero offset, obviously assuming closed loop stability. So hereafter we're going to assume that loops always have an integral, because it's nearly always the case that you want zero offset. What's the main content here then? This video is going to assume that we have a simple design like this, where we have a compensator M and a process G, and the compensator is going to take the form of a proportional plus an integral. You can see the proportional term here, Kp, and the integral term Ki over S. We're going to base our design on just two factors. We're going to look at speed of response, that's transient speed of response, and settling time. The heuristic guidance that we're going to give here are not formal. And the idea is they should give you answers which are close to a good solution, and from there you could do some fine-tuning to basically get better performance. However, if you want formal tuning guidelines for PI, you're probably going to cover this in a more advanced module, and you might come across things like Ziegler-Nichols, which is somewhat dated, but the most famous of those. Proportional design then. We want to focus on the concepts of over and under actuation, so we'll explain what we mean by that. Consider the point in time where a step change in the target happens. So what I'm going to do here is draw a target here, which you can see changes from 0 to R at time, and we'll just make it t equals 0 for convenience. Now, the output at this point would also have been 0. So what happens at the point where the target changes? And what you'll see is you're going to have an instantaneous error equal to R. So at t equals 0, the instantaneous error is going to match the target. So if your compensator is purely proportional, so you can see this block M is just Kp, then what are you going to have for U? You're going to have Kp times R. Now we also know that the desired steady state input is given as R over G of 0, the steady state gain. So what we're going to focus on here is comparing these two signals. What happens immediately that the target changes, and what is the steady state? So what can you see here? So if the steady state is bigger than the transient input, essentially what that means, just get rid of that so you can see, is that the K is small. U of 0 is small, and so you're going to have a slow response. But if the steady state is smaller than U of 0, that's telling you that K is large, U of 0 is large, and you're going to have a fast transient response. An illustration then. Look at the transient response here. And what's the key point? You can see what G of 0 is. It's 4 over 3. And you can see what Kp is. It's 2. So here, Kp is bigger than 1 over G of 0. And you see we get a large initial input, which is bigger than U steady state. And as a consequence, you can see we get a fast transient response. Not necessarily fast settling, but a fast transient. Look at the second example then. So now G of 0 is the same, it's 4 over 3, but this time Kp is 0.2. So here, Kp is much less than 1 over G of 0, and you can see I have a small initial input and a slow transient. So what's our observation? If Kp is bigger than 1 over G of 0, the initial input is larger than the desired steady state. So you're going to have an aggressive initial inputs, possibly you'll get instability and oscillation, and you're going to get fast transient behavior. However, if Kp is less than 1 over g of 0, the initial input is smaller than the desired steady state, so we would expect relatively slow transient behavior. Now, interesting thing which we didn't discuss and we're not going to is there's no clear link between the proportional gain and the settling time. You'll have seen in these examples actually the settling times are probably similar, irrespective of the transient speed. And in some cases, fast transients are not beneficial, and you could have a fast transient but still slow convergence. Now in practice, a value around 1 over g of 0 is likely to be reasonable, because that means you're not too slow and you're not over actuating. Integral design then. How do we understand the integral term? We're going to introduce this topic by encouraging students to think precisely about what the integral term is doing. It's integrating the error. So if you think you've got a block here, you've got the error coming in, you've got an integral there, what's coming out is the integral of the error. Now we can use this to derive a very simple but insightful formula. So the limit as time goes to infinity of u of t is going to depend upon the integral from 0 to infinity of e of t. I've given that a value a, and so you're going to find that we get this expression here. Ki times the area is u steady state. So if we just remove that again. So we know that the error is 0 asymptotically with integral, so we know that a is bounded, and therefore the steady state input is known. The steady state input is given by this formula here. Ki times the area equals USS. However, we also know that steady state depends upon the system steady state gain. USS equals R over G of 0. So we now have an additional formula, this one here, that Ki times the area equals R, that's the target, divided by G of 0. So this is a very insightful formula. The area of the error curve multiplied by Ki, see this product here, is a constant. Let's see how we can use this then. So notice here, this red area gives you the integral of the error. So this bit down here, this is the error between the target R and the output Y. So the red area is the area. And we've been told that essentially we've got this formula here, Ki times A equals USS. So if the area is going to be smaller, so if I want to make A smaller, then Ki has to be bigger. So if I draw a line to illustrate, here's a line that's made that area is now in here smaller. So if I make that area smaller, essentially I'm getting a faster response. So if Ki is bigger, I have the potential to get a faster response. And conversely, of course, if Ki is smaller, then the area has to increase. And so I've got slower convergence. How can I use these insights? So let's assume that the desired closed loop behavior is close to an ideal first order response with time constant t, which is what you can see in this graph. Now it's possible to show in that case that this area A is approximately RT. Now we've already got this formula here which we've derived, that USS equals R over G of 0 equals Ki times A. So all we need to do now is take this formula for A and plug it in here, and you end up with a new identity which tells you that in order to get a closed loop response with a time constant t, then Ki has to obey this identity here. So we now know approximately what value of integral gain is required to achieve a specified closed loop time constant. If Ki is bigger than that, you potentially could be faster. If Ki is smaller, you necessarily must be slower. So here's a summary of our heuristic guidance. So for the closed loop dynamic to be close to the open loop time constant, you notice here I'm going to assume t is now the open loop time constant, then I choose my PI compensators like this. 1 over G of 0 for Kp, and 1 over sg of 0 t for the integral term. If we want to be faster, then the proportional has to be larger, and also the ki has to be larger. So I can give myself a speed up factor of alpha and just multiply that on the formula like this. So you can see that to go faster than open loop by a factor alpha, I simply stick an alpha multiplying factor in there. Let's demonstrate how this works then. That's a reminder of our formula. So here's this system. We've got g equals 20 over 5s plus 1. So g of 0 is 20. So you'll notice in the formula I put 1 over g of 0 is 1 over 20. The time constant is 5. So I put 1 over 5. And in this case, I've got alpha equals 1. Now, if you look at these closed loop responses, what do you notice? We've got a nice smooth dynamic. The time constant t is indeed approximately close to 5, and this is the closed loop time constant. And also, if you look at the inputs, you'll see that the input pretty much goes straight to the steady state and stays there. So you're neither over-actuating nor under-actuating. Now, if you're wondering why we've got all of these different curves, it's because we've done some curves here with some uncertainty. So the actual system is not quite 20 over 5s plus 1. It might be 21 over 5s plus 1 or 20 over 5.5s plus 1. So we're just demonstrating that for some uncertainty in the model, this PI still gives behavior close to what you want. So the closed loop dynamic is close to the open loop dynamic and offset free tracking, even with some uncertainty. What about speed up? So you'll see here, I've said I want a speed up of a factor of 2. Same system, and you can see the initial input is now twice the steady state. So the steady state is down there, and the initial input here is twice as big. So that makes my transients twice as fast. And if you look at the implied time constant here, you can see it's twice as fast as on the previous slide. So the closed loop dynamic is twice as fast as the open loop dynamic, again with offset tracking and even with uncertainty. Now, what about second order examples? Now, for high order examples, the error curve has a different shape, and therefore the integral of the error is slightly different for a desired time constant t. And what you'll see is a particularly important one here is if you take a simple critically damped second order system, the integral of the error curve is now going to be 2RT, so it's twice as big as with a first order system. So that means that the required Ki has to be half as big. So that's a key observation, that you may need the Ki to be smaller if you have higher order systems. So here's an example. You can see I've taken a critically damped second order system. There it is. And what do you notice? The open loop response, nice and simple. The closed loop response has got some oscillation and overshoot, because with a simple heuristic PI, the integral gain is now a little bit too big. And you can see essentially the error integrates up too far, so the input ends up too high. You can see that here, and then you get a little bit of oscillation. Some conclusions then. We presented a heuristic PI design based on an understanding of key process attributes. So basically we exploit the steady state gain, open loop time constant, and a speed up factor alpha to say what do we want the closed loop time constant to be. This works very well with first order processes, but gives an integral gain that's slightly high for second order processes and indeed for higher order processes. Nevertheless, what will be clear to you is, although we've given you a simple design here which works okay for simple systems, you're going to need a more sophisticated and systematic set of tools for effective control design in general. Now, this is likely to form part of a more advanced or application course.